Welcome. The last class, I gave the first assignment of the course to go through and see if you could combine the components given on the chart up here to form compounds and give their names. Now, was that kind of an unfair assignment? Yeah, a little bit. The idea was to throw you in the midst of a variety of possible solutions and see how you did. Now, did I expect 100% success? Heck no. You need to understand in chemistry, just like life, you make a lot of failures before you succeed. So the key to success and the chance of improving your understanding of these concepts is to look at them and work at them. Now, today I'm going to take a few of these and put them together and show you what the compounds look like and what their names are. I recommend that you continue to use this chart, which is pretty overall encompassing, to provide you with compounds and their proper names. Now, are there others? Oh, heck yeah. But for now, this will give you an insight. Now, I'm going to start off by erasing the acids. I do trust you'll understand that the non-oxygen acids are column 1 and column 7 elements, or hydrogen rather, and column 7 elements combined. And their names are straightforward. The oxygen acids are a bit more tenuous as far as understanding their names, but there are very few of them. And sulfuric and nitric are the most important of these, and I would suggest you put those to memory. So we're going to start off by erasing the acids. And putting together some compounds. Now, I like to start off with polyatoms. And the polyatoms above will start out with ammonium, which is one of the few positive polyatoms, being a positive one. Now, just because I'm that kind of guy, let's mix it with something fairly complex, like the chromate ion. Now you look at it and you say, well, wait a minute, you got ammonium ion with a +1 charge and the chromate ion with a 2- charge, so that cannot possibly be the correct formula, and you would be right. The way you fix that is you multiply it. Now in compounds, the multipliers are put behind, and the name of this compound is ammonium. And then the chromate ion adds to it. Ammonium chromate. Now, is that difficult? Heck no. It's logical. Remember that in all sciences, logic dominates. If it's illogical, it's probably not going to work properly in science. Gear yourself to that right off the bat. Logic dominates. So if you got a +1 polyatom mixing with a -2 polyatom, you're going to, in essence, ensure that you need 2 of the +1s. And the name follows the logic of the name of the simple polyatoms that are used for the combination. The NH4 is ammonia, And when it's combined, it's ammonium. And the chromate remains just as it is as a polyatomic. Okay, we'll erase that. And try something a bit more interesting. We'll try calcium, which is a 2+ ion. And all of you who have actually done a little work on this recognize almost immediately that +2, -2, bingo, 0 works perfectly, and it is a pronounced compound. Now, the part of it that's moderately difficult is naming it. Well, calcium retains the name from the periodic table. And the C2O4 is oxalate. So calcium oxalate. Now, sometimes you have things that don't match up easily. For instance, every time you interject the phosphate ion, it's going to produce some repercussions because it's an odd ion with a 3- charge. For instance, if you're going to react it with a 2+, which would be magnesium, you can readily discern that magnesium and phosphate is not going to work out easily because you got a 2 and a 3. Now, your multipliers from behind work always. So the way to do that is cross multiply, as I call it. It's not accurate to phrase it that way, but that's the way I teach it. So you take your magnesium and you put a 3 behind that. You put a parenthesis around the phosphate and put a 2 behind that. Now what that does is it's 2 times 3 or 6 positives and 2 times 3 is 6 negatives, making magnesium magnesium phosphate. Now, what I've just done in a short period of time is illustrate some reasonably difficult ones. As far as the naming, some of them are pretty exotic. You see the ClO4 ion up there. That's perchlorate. You rarely see that in first semester general chemistry or even second semester general chemistry. So we'll probably not entertain it, but you should know that it exists. If you have this chart, again, I would get some cards. I recommended that when we were talking about size with my illustration on the board, that you put a card to it. Another card could, I recommend you have a periodic table of the elements, which you can acquire. You don't have to go out and buy it. If you got a color printer, you can download it from any of a number of websites for free. And then you have a periodic table of the elements. The coloration generally discerns whether they're gas or solid or liquid in their normal states, or uh, whether they're radioactive, or any of a number of things. But you need a chart of the periodic table of the elements. You need a size chart, and you need something that constitutes a kind of a cross-section of the polyatoms. Now, I've got a fairly decent cross-section here on the board, and if you want to just write those down on another card, that gives you 3 cards for reference that can push you in the right direction with this. Now, the next concept, which is, shall we say, not universally beloved, but as far as understanding goes, is the mole concept. So the next one that you're going to have to deal with is the mole concept.